In this video, we're going to be expanding on this equation that you learned for momentum, which was momentum equals mass times velocity. And to expand on this, we're going to take a look at situations where the car, if we take a look at a car going a certain speed, if we look at its mass times its velocity, we can find the object's momentum, p. But what if this car was to change its velocity, right? What if it was to get faster? So we'll draw a bigger vector for velocity here. If the car was to get faster, then its new momentum would be different than its old momentum, and we would have something called a change in momentum, delta p. This triangle p is how we're going to show that term, change in momentum. So whenever you see this triangle p, we're talking about change in momentum. There are a couple of equations that you need to know for change in momentum, and the easiest one that we use whenever we know how much the velocity has changed is going to be this one. Delta p, change in momentum, is equal to an object's mass times its change in velocity. So if you know how much the velocity changed, you can plug that into this variable right here, triangle v. Sometimes an object will get faster, as we talked about up here, and that would cause a positive change in momentum. So if an object was to get faster, its velocity was to get faster, then you'll end up with a positive change in momentum. And if an object was to get slower or slow down, then we would end up with a negative change in momentum. So sometimes in these values, if we end up with a negative as our change in momentum, that tells us that the object went slower. So this is the first equation you might have to use. And then there's a second one, and it still starts out with change in momentum. But right here, if we were to expand this with algebra, we could say that the object's change in momentum is dependent on its mass times its final velocity minus its mass times its initial velocity. These two things are the same. So m times vf minus m times vi will give you the same value as m times change in velocity, but sometimes we'll have to break it down like this second equation because we need to identify the specific velocity, how fast it was going at the end of its change or how fast it was going at the beginning of its change. So we're going to look at some examples where we have to use one or both of these equations depending on what the situation is. So let's take a look at this first example problem that we have. It says a car with a mass of 1,000 kilograms, so this 1,000 kilograms is going to be the mass, accelerates from rest to a speed or velocity of 30 meters per second. So the rest means that its initial speed was 0, and then its final speed, the VF, or the final velocity, was 30. We need to find the car's change in momentum, so they're asking us to find delta P. Now, when we look at this, we're trying to find delta P. We can use either equation to solve this problem. We can either use the first one, where it's just the mass of 1,000 times the change in velocity. How much did it change its velocity would go right here. Or you can use the second equation, where you do the mass times the final velocity minus the mass times the initial velocity. You don't generally have to use the second equation unless you're actually trying to find one of these individual velocities. So we're going to stick to the first equation for this problem right here. Now I've already identified the stuff that was given to us and the unknown, so the equation here is going to be triangle P is equal to m times the change in velocity. In this case, the change in velocity is just going to be the final velocity minus the initial velocity. So for us, that would be 30 minus 0, or 30. So that tells us how to find the change in velocity, right? We just take whatever its final velocity was of 30 minus what it started at, 0, and that tells us how much it changed. And now we're ready to plug our values into this equation. It would be change in momentum is equal to our mass of 1,000 kilograms times the change in velocity, which in this case is 30 meters per second. So 1,000 times 30 is going to give you 30,000 kilograms times meters per second as our change in momentum. And again, we use this equation, the simple one, because we're not trying to find what velocities the object was going at. We're just going to use the first equation and find its change in velocity by subtracting them. Taking a look at this second example, it says there's a firecracker with a mass of 2 kilograms. So this mass right here is our M. Is shot out from rest. So we know that its initial velocity is equal to 0. And it has a change in momentum of positive 7,000. So this value, positive 7,000, is actually our triangle P. It's the change in momentum. And they want us to find the final velocity. So this is an example where you're going to have to use that second equation because we're actually trying to find one of the velocities that's unknown, a VF in this case. So I'm going to go ahead and start by writing the equation. I've already shown what's given. We have our M, VI, delta P, and the equation that we're going to use is that second one. So it's going to be triangle P, or change in momentum, is equal to the mass times the final velocity minus the mass times the initial velocity. And when we plug in our values here for the substitution step, we're just going to go ahead and put our change in momentum, 7,000, is equal to our mass of 2 times our final velocity. We don't know that yet, we're trying to find it, minus our mass of 2 times our initial velocity, which was 0. So anything times 0 is going to be 0, so that's going to cancel this out. And we end up with just this part on the left, right? The 2 times the 0 is 0. So anything, if we're subtracting 0, it's like nothing. So we'll just get rid of it. And we're just left with this part on the left. So 7,000 equals 2 times the final velocity. And we've already seen with the previous momentum problems that if we're trying to isolate a variable, you do the opposite. If it's being multiplied, we're going to go ahead and divide by 2 on both sides. The 2's will cancel, and your final velocity here will be 3,500 meters per second. So this firecracker achieved really fast velocity after this change in momentum was applied to it. And again, the positive here tells us that it actually increased its velocity, so this answer makes sense that it went from 0 up to 3,500. If we had had a negative change in momentum, this object would have been slowing down. Okay, let's look at the next one. In this problem, it says a moose comes to a stop. So the final velocity here is 0 because it came to a stop. And it has a change in momentum of negative 2,000. So that's our delta P. And you know the mass of the moose was 2,000. That's the M. We need the initial velocity. They're asking us to find that. We're going to use that second equation. So change in momentum equals mass times final velocity minus the mass times the initial velocity. If we substitute our values from the word problem, it would be negative 2,000 is equal to the mass of 2,000 times 0 because we came to a stop minus the mass of 2,000 times the initial velocity. Anything times 0 is going to be 0, so that'll cancel this out. And you're left with negative 2,000 times VI equals negative 2,000. So to get the VI by itself, since it's being multiplied by negative 2,000, we'll divide it by negative 2,000. Do the same on both sides. this will cancel to 1, and you end up with your initial velocity is equal to negative 2,000 divided by negative 2,000, which we know is going to be 1 meters per second. So the moose had an initial speed of 1 meter per second, pretty slow, he's just walking, and he came to a stop with a change in momentum of negative 2,000. In these two problems, the velocities were 0, and it's not always going to be the case. In this last example, you'll see I've just actually skipped the word problem part and given you the given information. So in this one, if we're trying to find the change in momentum, and because we've already been given both velocities, we're going to use that first equation. So we're going to use change in momentum is equal to mass times change in velocity. Our change in velocity, we already talked about in the first problem, is going to be the final velocity minus the initial one. How fast were you going when you finished versus how fast you started? So in this case, it'll be 40 minus 20. So our change in velocity, how much we changed our speed, is just 20 meters per second. And our mass was 40, so if we were to substitute our numbers in here, it would be 40 times our change in speed, which was 20. So 40 times 20 is going to give us a change in momentum of 800 kilograms times meters per second. All right, now this is really important to understand that all these problems are going to start with those same two equations, but you can manipulate them to move them around and solve for different things. Just like we've been doing with algebra, you would pick the numbers that they gave you and plug them into the equation, and then manipulate the equation to solve for the unknown variable. So you could just as easily solve, if we were to take a look at this equation, let's say that they gave you a problem that said, hey, what is the mass? Well, if you don't know what the mass is, this one right here, then to get it by itself, you could divide both sides by the change in velocity. And then you'd end up with an equation for mass. Mass would be change in momentum divided by change in velocity. So there are sometimes problems where you'll have a situation like that. But they're all going to come down to these two equations we talked about. Sometimes it's convenient to use the first one, and sometimes it's convenient to use the second one. So if you watch this video, just know that you got to come prepared to class, and I appreciate you taking the time to watch it. It's going to be helpful and making you successful during class. Thank you for watching.